So in the last, Monday, Tuesday, Wednesday, and until now, we've covered a lot of stuff. Okay? There will be some information overload that nobody can control. We will have some additional, you might think, oh, there's so much of stuff and it didn't go into me all. That is fine. The idea is not to teach you anything about concrete. The key word is teach. I'm not teaching you anything about concrete. I'm introducing to you several things. And if you want to know that people know those things more closely, you have to create an association with them, right? I'm like a middleman, this matchmaker for marriages, right? Get the bride and groom together and I don't live with them, right? So I'll just introduce things to you and then you can use a lot of resources available to get more in-depth information on those things as you want, okay? So nobody can teach you or nobody can give you the entire gamut of what's there in concrete in 5 days. And it'll be a waste of all of our time. So far we focused primarily on things that happen at the very small scale, right? At some point of time we should say, okay, enough of this, give me the real thing. Give me the real concrete, give me ideas about what is happening at a larger scale. Now, the way I'm going to do it is, I'm going to give you the larger scale information about concrete as you see it normally without any of the sophisticated tools that we talked about over the last 3 days. Concrete as you see it, but with a link to what happens at a very small scale. On Tuesday, when I left you on Tuesday evening, I gave you 3 different things. Remember that at the end of the day, we talked about the composition of the chemistry of what you have in the system becoming the structure, the hydration products and the structure, right? The microstructure, which then relates to all your properties, whether whether it's durability or mechanical properties, all of that, right? And then I also said this is a 3-leg stool: composition and structure, properties, durability, mechanical properties, and the other leg of the stool is how you process it, how you work with the concrete, how you process it. So think of this as a 3-legged stool, each of those legs being very important and each of the legs being interconnected. So if you want to have a stable stool, you want to have all 3 of them and all 3 of them very well interconnected. So we talked a lot about composition and structure. I'm not going to talk to you much about processing because all of you know what that is, all of you know what you need to do. It's just that sometimes we don't do it right, but there's nothing to emphasize new in that. But we need to talk about properties and the link between structure and properties. How does structure influence properties of the concrete that we are going to deal with? So, before I have to talk about the properties and how the structure relates to properties. Now think of this carefully. When I'm talking about properties, I'm going to talk about mechanical properties and durability. Okay, and that's pretty much what you have in the system. But in the process of structure formation, which influences your properties, there is something else, which is your fresh stage in concrete, right? What happens when the concrete is fresh? Your microstructure forms only after the concrete sets and hardens and forms all the reaction products. So there is a fresh stage. So the processing part, I will just do a little bit with the fresh stage properties and I'll show you some rheological tools because I added this late because somebody asked about rheology. I don't know if you're okay. Somebody asked about rheology. So I'll quickly do a few things on rheology. Okay. Temperature, you always do it. Somebody talked to, yesterday I put this slide and somebody wanted to know how to do the setting time of concrete. So here is what it is. Pin penetration ASTM C403 is the test. Measurement of force required to cause a needle to penetrate 25 mm. So you do a pin penetration and then you look at initial and final setting time, look at penetration resistance. So 4000 psi corresponds to final setting. I think 500 psi corresponds to initial setting for concrete, not for cement. Cement you do the Vickett apparatus. Okay, workability, consistency. Again, I've done enough of slump bashing, so I'm not going to do that anymore. But again, slump is not a very preferred test. When you talk about workability of concrete, Workability is basically the amount of internal energy you need to produce full compaction, or the energy required to overcome the friction between particles. You want to make the concrete flow. Flowing of any particulate media is nothing but overcoming the frictional force between particles. Two aggregates together, very high friction, put in cement paste as a lubricant between them, friction goes down, right? So basically what you're doing is reducing the friction. So workability is a means in which you figure out how much of energy is required to overcome the friction between the particles, and consistency is the ease with which concrete flows. A lot of people mix these terms together and use workability and consistency together. They are not. Workability is the energy required to overcome the frictional forces. Consistency is the ease with which you can make the concrete flow. So slump does not measure workability. So anybody who tells you slump is a workability test is wrong. Slump test is wrong, and the fact that slump measures workability is wronger, if there's a word like that. Okay, it's even more wrong. So slump measures only consistency, ease with which your concrete can flow. That also it really doesn't measure, it gives you a fake measurement of what you think it happens, right? So this is what your slump measurement is. It does not give any measure of workability, it measures the consistency. So rheology is actually the study of flow, looking at intrinsic flow properties. So deformation of matter, rheology doesn't mean just flow alone. Any deformation of matter is rheology. 1920s is when the word was coined by Professor Bingham. All of you know Bingham fluids, Bingham law for rheology, all of that. Okay, so that's the guy. So flow is how liquids behave or respond to stress. Deformation is how solids respond or behave to stress. So very simply, this is something that always you should think about. You study fluid mechanics on one side, you study solid mechanics on the other side, and you think they are totally two different things. No, it's basically mechanics, and it's basically doing the same thing. Flow for a fluid is deformation for a solid. Because the solid has atoms so closely tied together with a very high internal energy, you cannot move them so much. Therefore, you can only deform them. A liquid has a very low internal energy. You can supply some amount of energy and make them flow very fast and very quickly. Therefore, that is deformation. So deformation is elastic response for a solid, right? Stress proportional to strain, elastic response. Similarly, flow is a viscous response of a fluid. Therefore, fluids are viscous. Concrete, because it's a combination of a fluid and a solid, is viscoelastic. If you have asphalt, it's way more viscoelastic because it's much more time and temperature dependent. Okay, simple laws just to quickly go through. Newton's law of viscosity for fluid, Hooke's law of elasticity for solids. You've seen all of these in your undergraduate class at some point of time. Stress is elastic modulus, whatever I just said G, could be E or G or whatever, times strain. Similarly, shear stress is viscosity times strain rate. Because it's time dependent, we do rate rather than absolute deformations or absolute strains. You have a strain rate. So gamma, when I put a dot on top of something, it just means it's d gamma over dt. It's just a rate of change of strain. So gamma dot is a shear rate, eta is a viscosity. Shear deformation, these pictures you've seen. So, think about flow of concrete. Don't think about the slump test. Think about flow. You have concrete flowing off the back of a truck through the chute, right? You can think of that. Now, if I think of a mass of concrete flowing down, can I represent that as several layers of concrete sliding one on top of each other? Can I consider it that way? That's what is happening, right? Several layers sliding on top of one another like this. But realistically, when it is sliding, which layer will have the highest velocity? The layer on the top will have the highest velocity. The layer on the bottom, for theoretical purposes, you can assume that there is a very thin boundary layer that assumes that stays constant, stays without moving. It slightly moves, but generally you can say that compared to the velocity of the top layer, velocity of the bottom layer is much lower. So you can create some kind of a liquid laminar idea where you have a force that's applied, it's flowing, and there is a velocity of flow. So viscosity is a property that enables it to yield continually under a constant shear stress. So you have a shear stress that's being applied to flow. If the fluid doesn't yield, which will it flow? No. You remember yielding, right? When you pull a piece of steel, you draw the stress strain curve of steel. You get to a point where the linear portion ends and the curve starts to deform. You call it the yield point. Why are you calling it the yield point? Why are you calling it yield? What's that? Why are you calling it yield? What is yielding? From an elastic material, you start plastic deformation. What is the characteristic feature of plastic deformation? It is irreversible. It cannot regain its position, regains original shape and deformation anymore. What else? What is happening? Therefore, if you cannot regain, what is happening? You have bond between atoms that are broken. Some of the atoms have plastic, you call it plastic flow, right? So even in steel, you call it plastic flow. Some of the atoms have moved away from their initial lattice positions, never to come back to those positions again. You have movement of atoms away from where they were supposed to be. You have plastic flow, so the material has yielded under that stress. When it yields, and that's what the yield stress that you use for all design purposes, right? Beyond which, for an elastic analysis, you have no use of that material. So, very similarly, if you assume that you have yielding, viscosity is that property which enables that yielding to happen, and the velocity gradient is equal to the shear rate. dV over dy is nothing but your gamma dot. Okay? Rate of change of velocity with respect to distance, which means very high velocity here, very low velocity here, so you will have a gradient, right? Higher at the top, lower at the bottom. So that gradient is dV over dy. And then you can do some math here. Just if you are interested in how the derivations are, you can look at it. So I'm assuming this layer to be not moving, this layer to be moving. Therefore, if I do an experiment in the lab, I will keep a stationary plate and I'll rotate the top plate, right? Or I'll keep a stationary plate and I'll slide the top plate. That's how you do rheology experiments. So you will get viscosity as stress over strain rate as opposed to stress over strain that you get for elasticity. Okay, so ideal, there are different types of materials. Ideal or a Newtonian material where the stress is proportional to strain rate directly. You can have, so that's a Newtonian fluid where shear stress increases linearly with shear rate starting from a 0 point. But concrete is not a Newtonian fluid. Water is a Newtonian fluid. Concrete is not a Newtonian fluid. Concrete, cement, paste are all what we call Bingham fluids. It's not strictly a Bingham fluid also, but we'll, for the time being, we'll assume it to be a Bingham fluid where you need to give it some energy, some critical energy beyond which, so you have to get it to some shear stress beyond which it will start to flow. You know, you can relate it back to the concept of activation energy I gave you earlier. You have to give it some energy to overcome a barrier. It's the same barrier it's trying to overcome. You see that? The same idea I gave you yesterday. It's overcoming the same activation energy barrier. You give energy, give energy, give energy. When it gets to a certain critical energy, you start to flow. Fracture of glass, fracture of brittle material, same thing. You get to a critical fracture length, a critical length beyond which glass will immediately fracture, right? Brittle materials will immediately fracture. So again, an activation energy concept where you have to give it certain energy beyond which it will flow well. So if you have a very dry concrete, you have to give it a lot of energy before it flows, and that lot of energy might not be used in flowing, it might be used in disintegrating the particles. Therefore, if you have a very low water cement ratio concrete or a very low slump concrete, more energy you give is detrimental because it's not flowing, it is just breaking apart. So you need to have the right material also for that to happen. So Newtonian fluid, I'll skip that. Viscosity, solid plus liquid, here are the models that you use, you've seen this, all of that. Spring and dashpot, in parallel it's a Kelvin model, spring and dashpot in series is a Voigt model. You can do all those mathematics for this, I'll skip all of that. Viscoelasticity, you have stress and strain and complex stress and complex strain, so everything is in complex plane. You have the real and imaginary parts of both elastic and elastic components. This is the real part, that is the storage modulus, that's the loss modulus or the viscous modulus, and then the loss angle tan delta, very similar to whatever you do with viscoelasticity, but again not very important. What really happens if you have a really elastic material, it's like bouncing a ball on a very hard surface. I bounce a ball on a hard surface, it will come back completely, right? Whereas a viscous material, when I bounce it, it won't come back because it would have lost a lot of energy, dissipated a lot of energy. So this is what you are dealing with when you are doing concrete rheology. You are dissipating a lot of energy. Different types of rheometers to do rheology testing. You can have a concentric cylinder, a cone and a plate, a parallel plate, torsion. You can have different geometries, but that's not important. The idea here is, think of a liquid in which you have particles suspended. So if you want to move, and then you can do different scales. You can think of whole concrete, which means what is a liquid in a concrete? Cement paste. And what is a solid? Aggregates. You take cement paste. What is a liquid? Water. What's a solid? Cement particle, right? So you have two length scales or two sets of length scales acting in the same material. So you have a rheology at the cement paste level, where the paste is sliding in this water medium, and then the whole paste and water acting homogeneously as a gel in which aggregates are trying to slide. So you have two optimizations you have to do when you do concrete rheology. And right now we really don't have to worry too much about it because we have really nice admixtures that will take care of doing all this what you have to by different chemical mechanisms, so that you don't have to spend too much time on seeing how this happens. But the idea is that you have to resist flow, and that's what you want. So if you have a Bingham fluid, your shear stress is an initial yield stress that you want to overcome, plus the viscosity times the shear rate. You have shear thinning fluids, you have shear thickening fluids, you have fluids that once you keep mixing shear thin, you have fluids that thicken with time. So a lot of different variants. Gel structure and suspension. So this is what admixtures do. When you have an initial structure, they're all bound together, and by both mixing as well as admixture action, you break the structure down, because you're not going to get these particles, for example, hydrate well in this state, but if you are like this, you will get good hydration. So rheology is also important for hydration. Good rheology of the paste is also important for hydration, because if the rheology is not good, you won't have water that's dispersed all through for good hydration. So microstructure formation is dependent on rheology. Okay? How does a microstructure form is a question of what is the rheology of your system. Okay. So here, initially when you have fresh concrete, it's almost towards the time of setting. Okay, initial state here, all, you know, aggregates and paste. Your yield stress of about 0.001 megapascal, plastic viscosity of 100 pascals per second roughly. After some more time, see the yield stress goes up by another order of magnitude, becomes about 10 kilopascal. Plastic viscosity becomes 500 pascal second. Further higher, yield stress becomes about 100 pascal, 100 kilopascal. Viscosity becomes 5000 pascal per 7, almost setting. So you have very different rates of change of. Can you put the AC on? Can somebody look at? It's very hot here. So for about 5000 pascal per second is when that kind of viscosity is, it's very difficult to move the system, and that's a very solid system. You can see here the picture also tells you here between the grains nothing has formed. You see a slightly thicker layer and then even thicker layer, so much more of structure formation. Onset of rigidity, styles, skip all of that. Okay. The other early age phenomena that you want to look at is dimensional stability in terms of shrinkage and creep. Okay. That also is, I consider this, and I'm going to put this together in the early age part itself so that we can cover this and then not worry about shrinkage and creep later. And then some people asked about creep and shrinkage, so I can cover this here itself. Volume changes are part of what you deal with in concrete. There is absolutely no concrete that does not change its volume. I gave you a very simple example. The cement itself, when it hydrates, changes to how many times its volume? 2 times its volume, roughly 2 times its volume, right? 1 grain of cement, when it hydrates, changes to about 2 times its volume. So you have a volume change that already happens. Now, think about what happens when volume changes happen in a material that is already in place. What happens when volume changes happen? Very fresh stage, when things are moving around, a change in volume can be easily adjusted internally, right? Because things are very fluid, change in volume is not going to be a problem. But also remember that every concrete structure that you ever build has some level of restraint. You are not building a concrete structure to be floating in air. Your concrete, if it's a pavement, it will be restrained by the base and the sub-base. If it's a beam, it's restrained by the column. If it's a column, it's restrained by the foundation and the walls on the side. So every concrete structure at any given point of time is always restrained. It's not free. Okay? So when you've restrained something and the volume change is not allowed to happen because you have held this in place, but the concrete really wants to change its volume, shrink because of reactions, what kind of stresses get generated? Tensile stresses get generated. And we all know that concrete is weak in tension. Actually, it is like if you remember what I said yesterday and day before, there is only tension, there is no compression really, right? Compression is what you apply. The material doesn't know there is something called compression. It knows only tension and shear. So you have tensile stresses. Tensile stresses start to come in and you get cracking. So that is the story of volume change in a nutshell. But that happens in a variety of different forms. First one is associated with thermal effects, associated with cooling. Very simply, heat of hydration, right? Very high heat, for example, if you are doing mass concrete, and then when it cools down, different parts of concrete will have a thermal gradient between themselves, right? The part that is in the middle has no place for the heat to go, so it will be very hot. The outside will be cold, therefore there will be a gradient of temperature. That gradient is enough for thermal stresses to happen. Now, the idea of stresses is an idea of irregularity. Stresses happen, again, when you uniformly impose a stress and the material has time to readjust to stress if it's uniformly imposed, you will have much lesser damage than stress gradients or thermal gradients that cause stresses. So thermal gradients cause a lot of stresses. Load or mechanical effects can cause stress. Drying or hygral effects with moisture loss can cause stress. Thin members, slabs, you will have a lot of stress because you will